Greetings and salutations, everybody. This is Jacob. Okay, so how the heck do we go about solving this problem? Seems discombobulating. Well, it's about as bewildering as it looks, my friends. No more and no less. I know that's not saying much. Complexity is in the eye of the beholder, as they say. What's one man's complexity is another man's simplicity. Oh, yes. All right, enough with vague talk. Let's get this show on the road, shall we? Let's start out by making some definitions. V of B is the speed of the boat, which is a constant. V of R is the speed of the river. B is the width of the river. T of C is the time it takes the boat to cross the river. U of T is the total speed of the boat, reinforced by the river. And theta is the angle at which the boat's trajectory forms with the starting riverbank. Okay, so now let's formulate mathematically T of C. Let's find U of T first. So as you can see here from this force sketch, U of T equals the square root of UB of x plus UR squared plus UB of y squared. And UBx is the x component of the speed of the boat, and UBy is the y component of the boat speed. So as you see here, cosine of theta equals UBx over UB, which is UBx equals UB times cosine of theta. And UBy equals UB times sine of theta. And we plug these two expressions into our first equation, and we get UT squared equals UB times cosine of theta plus UR squared plus UB squared times sine squared theta, which is UB squared times cosine squared theta plus 2 times UB times UR times cosine of theta plus UR squared plus UB squared times sine of squared theta. So that's U of T. So now let's turn our attention to T of C, the river crossing time. We have T of C equals D over U of T. And D is this distance here, as you see here, which is D equals B over sine of theta. So we plug that into our TC equation, and we get T of C equals B over U of T times sine of theta. And we'll square T of C so that we don't have to work with radicals in the derivative. We can do this because since T is above 0, then T of C and the square of T of C have their minimum at the same point, theta. So T squared of C equals B squared over UT squared times sine squared theta, which is this expression here. And we simplify this expression to T squared C equals B squared times UB squared times sine squared theta plus 2 times UB times UR times sine squared theta times cosine theta plus UR squared times sine of squared theta. And all of this is to the power of -1. And this is our T squared C with respect to theta. So how do we minimize this function? You guessed it, my friends. Take the derivative of it and equate it to 0. So let's do just that, using the power rule and the product rule of differentiation. So we have T squared of C prime of theta equals this long expression here. So we obtain this expression using the power and a product rule. We brought the power of the expression down by 1, brought the previous exponent in front of the coefficient B squared times the derivative of the inside, which is the power rule. We use the product rule to obtain the derivative of the inside. So we simplify this expression using algebraic manipulations. We factor out sine of theta out of the derivative of the inside. And to equate this entire function to 0, all we have to do is equate the stuff that's in the parentheses to 0, which is 2 times UB squared times cosine theta plus 4 times UB times UR times cosine squared theta minus 2 times UB times UR times sine squared theta. And sine squared theta we're going to rewrite as 1 minus cosine squared theta plus 2 times UR squared times cosine of theta. And we equate that to 0. And we rewrite this equation to match the general form of a quadratic equation. And we end up with 3 times UB times UR cosine squared theta plus UB squared plus UR squared times cosine theta plus negative UB times UR, which is 0. And the square root of this quadratic equation is cosine of theta equals minus UB squared minus UR squared plus or minus square root of UB to the 4th power plus UR to the 4th power plus 14 times UB squared times UR squared. And this is all over 6 times UB times UR. And we only use the plus sign here. Otherwise, this whole expression will be negative. And it makes little physical sense, because if cosine of theta is negative, then theta is above 90 degrees, which makes little physical sense. Hence, we only use the plus sign in our expression. And this is a good time to start plugging in our numbers, our initial conditions, because we can only go so far working symbolically, because the formula is going to be pretty complicated, my friends. So what do our initial conditions say? They say that the speed of the river is 20 kilometers per hour, the speed of the boat is 12 kilometers per hour, the width of the river is 30 kilometers, and so we plug those numbers in our cosine theta formula, and we end up with cosine of theta equals 0.312, which is theta equals arc cosine of 0.312, which is approximately 71.82 degrees. So now we found the optimal angle at which the boat should travel in order to get to the other side of the river in the shortest time possible. Regardless of where it ends up, we don't care where it ends up as long as it ends up on the other side. So now we go back to our TC function. We don't plug this value in TC squared, but in TC. We plug all our numbers in that equation and we end up with TC equals 1.2 hours, which is 1 hour and 12 minutes. And that's your answer. 1.2 hours. It's a bit less time than I expected, to be honest with you, my friends. Oh, yes. The answer is a bit counterintuitive, which I always like that, when the answers are a bit counterintuitive. Wow, what a problem, you guys. There's no shortage of great and interesting calculus puzzles to sink your teeth into, my friends. The genre of optimization is quite fascinating to me. I don't know about you, but it's quite fascinating to me. This is a special case of Euler's navigational problem, by the way, where the velocity of the river is constant, but in Euler's navigation problem, the speed of the river varies depending on where the boat is. So in that instance, the optimal path isn't a straight line, but a curve. And so the methods of the calculus of variations are needed to solve that problem. And I'll make a video on that in the future. But today I wanted to cover this special, simpler case that can be solved with regular calculus, just to get our feet wet, pun not intended, as a light introduction to Euler's navigation problem. And there are ways to beef up this problem, of course, some of which require variational calculus, and some that don't. You can make the banks into curves, for example. You can have the boat arrive at a specific place on the other bank, what we call a fixed endpoint problem. In this case we solved today, we don't actually care where we end up on the other side, as long as we cross the river in the shortest possible time. What we call a problem with a variable endpoint. So yeah, just like the snowplow problem, the sky is the limit. You can conjure up as many scenarios as you like. That's pretty much it, my friends. Let me know in the comments if you liked this puzzle, if you found it difficult. As always, send a puzzle suggestion my way. Smash those buttons like your life depended on it. I'll see you guys in the next video. Bye-bye.